All right, let's jump right in. We are absolutely surrounded by numbers every single day, right? But I mean, have you ever really stopped to think about the story behind one of them? The incredible hidden journey of physics and engineering it takes for just a single, simple number to pop up on a screen? Well, today, we're going to unravel one of those stories.
So, picture this. You're deep in the heart of a massive container ship, in the engine control room. It's loud, it's humming with power. And right there on a brightly lit control panel, you see this. Fuel service tank 1, 92%. Seems simple enough, doesn't it? But trust me, that one number is the very last word in a long, pretty fascinating conversation that's happening deep inside the ship's machinery.
So, that's our big mystery for today. Where does this number actually come from? Because it doesn't just magically appear. Nope. It's carried from the guts of a giant steel tank by a totally invisible messenger. It's translated from a physical force, and get this, it even has a secret ingredient that can change what it means entirely.
To figure this all out, let's work backwards, starting from the screen. That 92%, it has to travel from the tank all the way to the control room. It does that as an electrical signal, but not just any signal. It's a very special kind, one that's perfectly built for the noisy, demanding world of a ship's engine room.
Okay, meet our invisible messenger, the 4 to 20 milliamp current loop. Now the keyword here is current, not voltage. See, in the world of industrial automation, sending a steady current is just way more reliable. It's kind of like sending a message with a constant, strong push, instead of a shout that can just fade out over a long distance. And this is what's so cool about it. The system is just so simple and elegant. It's a straight line, a perfect scale. When the tank is bone dry, completely empty, the system sends 4 milliamps. When it's totally full, it sends 20, and every single level in between corresponds to a specific current. So, a half-full tank? You guessed it, that's exactly 12 milliamps. It's simple, direct, and incredibly reliable.
So why go to all this trouble? Well, an engine room is a gray, brutal place for sensitive electronics. You've got massive machinery creating a ton of electrical interference, basically noise. A signal based on voltage can get totally messed up by all that static. But a current loop, it just powers right through it all, even over super long cables, delivering a clean, accurate message every single time.
Okay, so now we know how the message travels. But how does our little messenger know what to say in the first place? How does an electrical system know the physical level of fuel that's sloshing around inside a giant steel tank? Well, for that, we have to go inside the tank itself. And here it is, our first major plot twist. The system isn't some kind of magical dipstick. It doesn't actually measure the fuel level directly, not at all. Instead, it measures something else entirely. The pressure at the very, very bottom of the tank.
This whole thing works because of a really basic principle of physics. You see, the column of fuel in the tank has weight, and all that weight presses down, creating what we call hydrostatic pressure. So the more fuel you have, the taller that column is, the heavier it gets, and the greater the pressure is at the bottom. The system uses this pressure as a stand-in, a direct proxy for the level.
Now you might be thinking, great, mystery solved, pressure equals level, simple. But it's not quite that easy. There's one more critical variable in this whole equation. It's a hidden property of the fuel itself that can throw the entire measurement way off if you don't account for it.
And that variable is called specific gravity, or SG for short. Now, in simple terms, it's just a measure of how dense or how heavy a liquid is compared to water. A liquid with a higher SG is just heavier for the same amount of volume. And for our fuel measurement, this is absolutely crucial.
You see, not all marine fuels are the same. A lighter marine diesel oil has a lower SG, while that thick, almost syrupy, heavy fuel oil is much, much denser. Sometimes it's even denser than water. And that difference, well, that difference changes everything.
And here it is. This is the big aha moment. I want you to imagine two tanks, both filled to the exact same level. One's got that light diesel, the other's got the heavy fuel oil. Well, because the heavy fuel is denser, its weight creates more hydrostatic pressure at the bottom, even though the level in both tanks is identical. Same level, different pressure.
This is why that twist matters so much. If your system is calibrated for diesel, but you fill the tank up with heavy fuel, it's going to sense that higher pressure and think the tank is way more full than it actually is. It's lying to you. So an engineer has to know the specific gravity of the fuel they're using and calibrate the system for it. Otherwise, that number on the screen is meaningless.
So now we have all the pieces of the puzzle, right?
We've got the fuel itself, the pressure it creates, that secret ingredient of specific gravity, and the invisible messenger that carries the final report to the crew. Let's put it all together and see the full picture.
So the journey is this beautiful chain of events. First, the physical fuel in the tank creates hydrostatic pressure. A transmitter at the bottom of the tank measures this pressure, and it has to be carefully programmed for the fuel's specific gravity. Then, it converts that pressure reading into a super precise 420 milliamp electrical signal. That signal travels through the wires all the way to the engine control room and finally becomes the number we see on the screen.
And look, this isn't just some neat engineering trick. That number, that 92%, it's a lifeline. The fuel oil service tank supplies fuel directly to the ship's massive engines. If this reading is wrong and that tank unexpectedly runs dry, the engine's shut down. And an engine shutdown in the middle of the ocean is a catastrophic failure.
And that signal does way more than just power a display. It's also a watchdog. It's tied directly into the ship's alarm system. So, if the current drops to around 8 milliamps, a low-level alarm starts blaring, warning the crew to take action. If it rises to about 18 milliamps, a high-level alarm goes off to prevent a messy overflow. It's a proactive safety system, all built into that one signal.
Of course, in the real world, things can and do go wrong. A good engineer has to basically be a detective, troubleshooting everything from incorrect SG settings and blocked sensor lines to how the outside temperature might be changing the fuel's density. Understanding this entire chain, from physics to electronics, is what really separates a good engineer from a great one.
And this quote from the source material just sums it all up perfectly. When you see that fuel level in the control room, you are not just seeing a number. You're seeing the end result of a physical process, liquid physics, translated through layer upon layer of engineering into one single critical piece of information.
So the next time you see a percentage on a screen, or a temperature on your thermostat, or even the speed on your dashboard, remember this journey. Think about it. What invisible messengers and what hidden variables had to be perfectly lined up just to bring that simple number to you? What other incredible stories are hiding right there in plain sight?